Hello, teachers and students. My name is Liu Qing. What I am reporting today is millimeter wave hybrid precoding algorithm based on deep learning. I will introduce from 5 aspects: research background, problem description, neural networks, simulation results, and conclusion. Part 1. Research background. In the context of millimeter wave massive MIMO systems, although a lot of research has been done to enhance the performance of hybrid precoding, there are still many problems. The two main challenges are high cost and poor system performance. Therefore, we proposed a millimeter wave hybrid precoding method based on deep learning, which jointly optimizes the China measurement vector and designs a hybrid beamforming vector to achieve a near optimal data rate with negligible training overhead. Part 2. Problem description. The fully connected hybrid architecture depicted in Figure 1. Next to Figure 1, we give the China model of this paper and introduce some parameters in the model. We use ULA as our antenna array. The overall goal of this paper is to directly design hybrid precoders combinators to maximize the rate of system implementation. So, there are two main steps to realize. Firstly, if the channel is known and the RF beamforming combinator vector is selected from the predefined quantization codebook, the hybrid precoding combinator design problem can be expressed as Formula 1. If the RF beamforming combined codebook consists of orthogonal vectors, such as the DFT codebook, then for any selected RF precoder and RF combiner, the best baseband precoder combiner is expressed as Formula 2 and 3. Then, the optimal hybrid precoder can be found through exhaustive search of candidate RF beamforming combination vectors, which means the hybrid precoding design problem can be transformed into an exhaustive search problem of RF precoding combination matrix, which can be expressed as Formula 4. Part 3. Neural networks. The structure of the cascaded hybrid precoder we proposed is mainly composed of two parts: China encoder and precoder, as shown in Figure 2. China encoder is composed of two parallel convolution modules. This module is inspired by inception module in GoogleNet architecture. The convolution in the inception module is modified to a two-dimensional complex convolution. The first module is shown in Figure 3, which contains 3 complex convolution blocks with kernel sizes of MBS 12 and 10. 2 blocks with kernel sizes of 12 and 10 are connected behind the complex convolution block to reduce the dimensionality. The second module is shown in Figure 4, which contains 3 complex convolution blocks with kernel sizes of 6, 5, and 4. precoder consists of 2 fully connected layers and 2 output layers, which takes the output of the channel encoder as input. Through 2 fully connected layers and a fully connected layer maps the learned distributed feature representation to the sample label space for classification. Sigmod activation and benchmark standardization are performed after each fully connected layer. Next, I will introduce how to train and predict neural networks. In the training stage, the cascade hybrid precoder performs end-to-end training in a supervised manner. The training process is shown in Table 1. Firstly, the dataset of millimeter wave channels and the corresponding RF beamforming combination matrix are constructed. And then the cascade hybrid precoder is trained to be able to predict the index of RF precoding combination vectors given the input channel vector. After the neural network is trained, the trained neural network is used to design the hybrid precoding matrix. The prediction process is shown in Table 2. Next, we use the tracing model for simulation. The dataset uses a publicly available general deep MIMO dataset to generate simulation parameters. Figure 5 shows the relationship between the achievable rate of the proposed cascaded precoding and the total transmit power when the channel measurement value is equal to 2, 4, and 8. It can be seen from the figure that the performance of the proposed cascaded precoder is close to the upper limit under a reasonable transmit power value. Additionally, compared with the traditional hybrid precoding method, the training overhead is significantly reduced. Figure 6 shows the relationship between the achievable rate and the total transmit power of the cascaded hybrid precoder, the spatial sparse precoding method, and the automatic precoder. It can be seen from the figure that, in all the schemes, the achievable rate increases as the total transmit power increases. In addition, the performance of the cascaded hybrid precoding scheme is better than that of the automatic precoder. When total transmit power increases, the performance gap becomes larger and larger. Figure 7 shows the relationship between the achievable rate and the total transmit power for different learning rates. It can be seen from the figure that the proposed cascaded precoding is optimized by a lower learning rate, because a higher learning rate will lead to a higher verification error. However, the convergence speed will be slower due to the lower learning rate. Therefore, the optimal learning rate should be selected reasonably to achieve better performance. So, we set the learning rate to 0.01. In addition, we also give the classification accuracy of the analog precoding vector at the base station, the analog combined vector at the user end under different total transmit powers, as shown in Table 3. It can be seen that The accuracy for the transmit and received predicted beings are almost the same, since we treat them as equally important tasks when training the auto precoder neural network model. Besides, the classification accuracy of the cascaded precoder increases continuously with the increases of the total transmit power when the number of channel measurement vectors remains. That because a larger number of pilots can obtain more channel state information, which makes the neural network use more features for classification during training. However, when the number of pilots continues to increase, the classification accuracy tends to stabilize, whose value stabilizes at 0.94. Figure 8 shows the relationship between the classification accuracy of the proposed cascaded precoder and auto precoder methods with different total transmit power. It can be seen from the figure that the classification accuracy of these two schemes increases with the increase of the total transmission power. The classification accuracy of the cascaded precoder is better than that of the auto precoder. In addition, the stability of cascaded hybrid precoder is better than that of automatic precoder. Classification accuracy is significantly improved, especially with less pilots. Figure 9 shows the relationship between the size of the cascaded precoding loss function and the number of iterations. It can be seen that the loss function curve changes smoothly on the training set and the test set without excessive fluctuation or jaggedness, which indicates that the learning rate set is reasonable and it is close to the constant raw view under a limited number of iterations. There is no obvious gap between the loss function of the training set and the loss function of the test set, indicating that the network does not appear underfitting and overfitting. In conclusion, we proposed a cascade hybrid precoding algorithm based on deep learning for millimeter wave hybrid precoding. Cascaded hybrid precoder learns how to optimize channel sensing vectors to concentrate sensing power in the direction most desired, and how to predict RF beamforming and combination vectors of hybrid architectures directly from the received sensing vectors. Combined with the traditional method, the proposed deep learning method can directly predict the simulated precoding or combination vector under the condition of unknown channel state information, which overcomes the huge training cost required to select the optimal beamforming vector in the large antenna array millimeter wave system. At the same time, the data rate is close to the best data bit rate. Compared with some existing deep learning schemes, the performance of cascaded hybrid precoding is closer to that of all digital precoding algorithm, and it can accurately predict the analog precoding matrix or combination matrix with fewer channel measurement victories. That's all for my report. Thank you for your listening.